A Nobel Prize winner looked at exploding stars millions of light years away and found that the universe is breaking its own rules. Space is expanding, and instead of slowing down, it is speeding up. Something invisible is pushing every galaxy away from every other galaxy, growing stronger as it goes. We are going to find out what that force is, why it terrifies physicists, and what it means for the fate of every single thing that exists. If you enjoy the journey, like and subscribe. Let's go. Saul Perlmutter was not supposed to change everything. He was just supposed to measure how fast the universe was slowing down. That was the job. In the late 1990s, Perlmutter led a team of astronomers at Berkeley. Their mission sounded simple. Look at distant exploding stars, measure how far away they were, and calculate how much gravity had been pulling the brakes on the universe since the Big Bang. Everyone expected the answer to be a number, a clean, satisfying number that confirmed what physics had always taught. Gravity pulls things together. The Big Bang sent everything flying outward, so the expansion of the universe had to be slowing down. That was not a guess. That was bedrock. That was the kind of thing written in textbooks without a question mark. Perlmutter's team spent years building the tools to prove it. They hunted for a specific type of exploding star called a supernova. These explosions are so bright they can outshine an entire galaxy for a few weeks. And here is the useful part. Every single one of them explodes with almost exactly the same brightness. That makes them perfect measuring sticks. If you know how bright something really is, and you see how dim it looks from Earth, you can calculate exactly how far away it is. Simple geometry, reliable physics. So the team found their supernovae, dozens of them, scattered across billions of light years. They measured the brightness, they ran the numbers, and the numbers came back wrong. The distant supernovae were dimmer than they should have been. Way dimmer. That meant they were farther away than the model predicted. And the only way they could be farther away was if the universe had been expanding faster in the past than anyone expected. Perlmutter stared at the data. His team stared at the data. Then they did what any good scientist does when the universe hands them something impossible. They assumed they had made a mistake. They checked the telescopes. They checked the calculations. They checked for dust clouds that might be dimming the light. They checked for errors in how they identified the supernovae. They rebuilt the analysis from scratch. Same answer every time. The universe was not slowing down. Something was pushing it to expand faster and faster. Every second, every galaxy was being shoved further from every other galaxy by a force that had no name and no explanation. And it had apparently been doing this for billions of years without anyone noticing. This was the moment physics cracked. One dataset, one team, one sleepless night in California, and suddenly the rule that had held since Einstein was gone. The universe was accelerating, and nobody knew why. Perlmutter's team published their findings in 1999. The response from the scientific world was not celebration, it was suspicion. Physicists pushed back hard. They demanded the data be checked again. They proposed alternative explanations. They did everything they could to make the result go away. It did not go away. And here is where the story gets stranger, because at the exact same moment Perlmutter's team was staring at their impossible numbers, a second team on the other side of the world was staring at the exact same thing. Same supernovae, same dimness, same result. Two rival teams, one impossible discovery, zero explanations. The universe had just handed science its biggest mystery in a century, and the scientists holding it had no idea what they were looking at. They just knew one thing for certain. The old rule was dead. What replaced it would terrify them even more. For most of human history, the universe seemed obvious. Things fall down. Planets circle the sun. Galaxies hold together. All of it happens because of gravity, the one force that reaches across every distance, never switches off, and only ever pulls. Gravity was the universe's thermostat. It set the rules, and for centuries, those rules felt permanent. When Edwin Hubble confirmed in 1929 that the universe was expanding, that did not break the rule, it extended it. Sure, Galaxies were flying apart from the Big Bang, but gravity was still working, still pulling, still slowing everything down. The expansion was just a race between the outward blast of the Big Bang and the inward tug of all that mass. Gravity had to win eventually, or at least fight the expansion to a draw. Every cosmology textbook written between 1930 and 1990 said the same thing. The universe is expanding, and gravity is putting on the brakes. The only question was how strong those brakes were. Physicists had a name for the key measurement they needed. They called it the deceleration parameter. Notice the word deceleration, slowing down. That word was baked into the very name of the thing they were measuring. The assumption was so solid, so obvious, so universally agreed upon that it shaped the vocabulary of the entire field. Scientists split into two camps. One camp thought gravity was strong enough to eventually stop the expansion entirely, then pull everything back together in a massive collapse. The other camp thought gravity was just weak enough that the universe would expand forever, but slower and slower until it barely moved. Both camps agreed on the core idea. Gravity was in charge, and the universe was decelerating. Imagine throwing a ball straight up. It goes up fast, then slower, then it stops, then it falls. That is what everyone expected the universe to do. Some thought it would fall back. Some thought it would just stop rising and hover. But everyone agreed it was rising more slowly every second. This picture felt safe because it matched everything else in physics. Mass attracts mass. More mass means stronger attraction. The universe is full of mass, so the brakes had to exist. The deceleration parameter was supposed to be a positive number, a clean confirmation, a number that finally told humanity how the universe would end. When Perlmutter's team calculated it, they got a negative number. Negative. The universe was accelerating. The ball was going up and somehow getting faster instead of slower. That is not a small discrepancy. That is a different universe than the one every equation had been built to describe. The rule that everyone trusted, the one that had survived every test for decades, had simply never been tested at the right scale. Nobody had looked far enough away, far enough back in time. The local universe, the part we can see easily, behaved just fine. Gravity appeared to be doing its job, but zoom out far enough, look at galaxies billions of light years away, and something else was in control, something that laughed at gravity. And the scary part is that this something was not hiding. It had been there the whole time, filling every inch of empty space, pushing outward from inside the universe itself, growing stronger as the universe grew larger. Nobody had ever felt it because nobody had looked hard enough, until two teams did, simultaneously, and the answer they both found pointed toward a force that had no place in any equation, any model, or any theory. But before we get to what that force might be, we need to understand the tool that exposed it, because without a very specific kind of exploding star, none of this ever gets discovered. Picture a star so bright it outshines 4 billion suns. For a few weeks, one single explosion lights up an entire galaxy. Then it fades, gone. Just a scar of hot gas drifting through space. That explosion is called a Type Ia supernova, and it is the most useful measuring tool in the history of astronomy. Here is why. Most things in space vary wildly. Stars come in different sizes, different brightnesses, different colors. Trying to use a random star as a distance marker is like trying to measure a room using candles of unknown sizes. One candle might be a birthday candle. Another might be a floodlight. You cannot compare them. A Type Ia supernova is different. Every single one of them explodes with almost the same peak brightness. The reason goes back to how they form. A white dwarf, the dense dead core of an old star, pulls material from a companion star nearby. It keeps pulling until it hits a specific mass threshold, about 1.4 times the mass of our Sunday. At that exact point, it ignites. The explosion is triggered by the same physical limit every single time. Same trigger, same explosion, same brightness. Astronomers call them standard candles. If every candle in that room were identical, you could stand anywhere and calculate exactly how far away each one was, just by how bright it looked to you. Dim means far, bright means close. The math is exact. Perlmutter's team used this trick on a cosmic scale. They searched for Type Ia supernovae in galaxies billions of light years away. When they found one, they measured its brightness. Then they compared that brightness to what it should look like at various distances. From that, they could calculate precisely how far away the galaxy was. And they could do something else. They could measure the redshift of that galaxy's light. As the universe expands, it stretches light traveling through it. The longer the light travels, the more it stretches, pushing toward the red end of the spectrum. The amount of stretching tells you how much the universe has expanded since that light was emitted. Put the distance and the redshift together, and you get a snapshot of how fast the universe was expanding at a specific moment in the past. String enough of those snapshots together and you get a movie of the universe's expansion history. That movie showed something nobody expected. The early universe expanded fast, then seemed to slow, and then started speeding up again about 5 billion years ago. Around the same time our solar system was forming, the universe shifted gears. The brakes stopped working. Something else took over. The tool was reliable. The data was clean. The conclusion was inescapable. But here is the part that nobody talks about enough. This discovery almost did not happen. For years, hunting supernovae was brutal. You had to scan thousands of galaxies, wait for one to explode, catch it at peak brightness within days, and then measure it before it faded. The whole thing required military-level scheduling of telescope time across multiple countries. Perlmutter's team spent years building that system. They were exhausted, underfunded, and operating on a shoestring. And the result they got for all that effort was data that made no sense. The stars they had trusted completely were now telling them something that broke physics. And a second team, working in secret on the other side of the planet, was about to confirm every impossible word of it. Brian Schmidt did not like Saul Perlmutter. That is not a rumor. In science, competition is real. And in the late 1990s, two teams were in a full sprint to be the first to measure the universe's deceleration. Perlmutter led the Supernova Cosmology Project out of Berkeley. Schmidt led the High-Z Supernova Search Team, a group scattered across the United States and Australia. They were chasing the same exploding stars, using the same logic, aiming for the same prize. And both teams were absolutely certain that the other team was going to make an error somewhere, and they were going to be the ones to get it right. Schmidt's team moved fast. They were scrappy, aggressive, and deeply motivated to beat Berkeley. They found their supernovae. They measured the brightness. They ran the numbers. And they got the same wrong answer. The supernovae were too dim. The universe was too big. The expansion was accelerating. Schmidt called his lead data analyst, Adam Rees, who had been quietly crunching the numbers from his office. Rees had built a more careful statistical model than anyone else on either team. He had cross-checked everything. He had looked for errors, for biases, for any way the data could be wrong. His conclusion was the same. The universe was speeding up. When Schmidt got the call, he later said he felt sick. He used almost exactly that word. The result was so strange, so far outside what anyone expected, that his first instinct was that something had gone terribly wrong. He told Rees to check again. Rees checked again, same answer. Here is what made this moment historic. Two rival teams, competing against each other with totally separate datasets, using different telescopes on different continents, both arrived at the same result at almost the same time. In science, that is as close to airtight as it gets. One team finding something weird is a possible error. Two rival teams finding the exact same weird thing independently is a discovery. Both teams published in 1998 and 1999. The physics world went into shock. Then slowly, reluctantly, it accepted what the data said. In 2011, Perlmutter, Schmidt, and Rees shared the Nobel Prize in Physics. The committee said they had discovered one of the greatest mysteries in science, the accelerating expansion of the universe. But notice what winning the Nobel Prize did not do. It did not explain anything. The award recognized the discovery. The cause remained completely unknown. Something was pushing the universe apart faster and faster. Something that existed everywhere, in every cubic inch of empty space, in the gaps between galaxies, in the void between stars, in the air between your fingertips right now. Invisible, unmeasurable, everywhere. Scientists gave it a name because that is what scientists do when they find something they cannot explain. They named it dark energy, and the name tells you everything about how well we understand it. Dark means we cannot see it. Energy means we know it does something. That is the full extent of our knowledge, a name for a blank space in our understanding. The discovery that won the Nobel Prize was really a discovery of how much we do not know, and what we do not know is the majority of everything. Imagine you throw a ball straight up into the sky. It rises, it slows down, gravity pulls it back, it falls. Everyone has seen this, everyone knows this. It is one of the first things humans learn about how the world works. Now, imagine the ball goes up, and instead of slowing, it speeds up, not because you threw it harder. The throw already happened. The ball just decides, on its own, to go faster the higher it gets. And the higher it goes, the faster it accelerates. Forever, that is what the universe is doing right now. Every galaxy is the ball. The Big Bang was the throw. And something is making every galaxy move away from every other galaxy faster and faster as time goes on. The farther apart they are, the harder this force pushes. People hear, the universe is expanding, and picture something like a balloon being inflated. That image is useful, but it misses the most shocking part. A balloon expanding at a steady rate is strange enough. A balloon that somehow inflates faster every second, with no one blowing into it, for no physical reason anyone can identify. That is something else entirely. The technical term for what is happening is accelerated expansion. Cosmologists measure it using a number called the Hubble constant, which describes how fast the universe is expanding right now. They also look at how that number has changed over time, and what they find is that the expansion rate was actually slower in the past. About 5 billion years ago, something flipped a switch. Before that point, the universe's expansion was decelerating, just like everyone expected. Gravity was doing its job. Then, roughly when our solar system was beginning to form from a cloud of gas and dust, the expansion started speeding up. The timing is haunting. While the ingredients for Earth were clumping together in one small corner of the Milky Way, the universe itself was changing behavior. A new force was winning, and it has been winning ever since. To picture what this means at cosmic scales, consider the Andromeda Galaxy. Right now, it is moving toward us because local gravity is stronger than the expansion at this short distance, only 2.5 million light-years away. But galaxies farther out are moving away from us, and the ones even farther out are moving away faster. And the ones at the edge of the observable universe are moving away so fast that the light from them will never reach us. They are, in a very real sense, leaving our universe forever. Every year that passes, more galaxies cross that horizon, more light disappears. The universe we can observe is shrinking, even as the universe itself is growing. In 1 trillion years, if any intelligent life exists, they will look out into space and see almost nothing. Every other galaxy will be gone. The sky will be nearly empty. They will have no way of knowing there was ever anything out there at all. The evidence will have vanished. Dark energy is not just changing the universe's speed. It is changing what the universe will ever be able to know about itself. And we still do not know what dark energy is. We know it is there. We know it is winning. We know it is getting stronger. But the force behind one of the most dramatic changes in cosmic history has no confirmed identity. What fills that space instead is a name, a question, and a number that makes physicists lose sleep. Every cubic inch of empty space contains it. The gap between your hands right now, the air above your head, the space between Earth and the Moon, the void between galaxies, all of it packed with a form of energy that pushes outward, never fades, and grows more powerful as the universe expands. And nobody has ever detected it directly. Ever. Dark energy is the name scientists gave to whatever is causing the universe's accelerating expansion. The name sounds dramatic. It is actually an admission of ignorance. Dark means invisible, undetected, unknown. Energy means it behaves like energy in the equations. Together, the name means something with the mathematical properties of energy that we cannot see and cannot explain. Here is what makes it genuinely strange. Ordinary energy, the kind in a battery or a stick of dynamite, is stuff. It exists somewhere. It runs out. Dark energy does the opposite. As the universe expands and space grows larger, dark energy does not spread thin. It stays at the same density. More space appears, and dark energy fills it instantly, at full strength, as if space itself is generating it. That behavior breaks every intuition about how energy works. To understand how much dark energy dominates the universe, think of everything you have ever seen or heard or touched. Every planet, every star, every galaxy, every black hole, every atom in every human body. All of that, every single thing made of ordinary matter, makes up about 5% of the universe's total energy content. Dark matter, another invisible mystery, makes up around 27%. Dark energy makes up the remaining 68%. Roughly 7 out of every 10 units of energy in the universe is this invisible, unexplained force that we discovered less than 30 years ago. The universe is mostly something we have never touched, never seen, and have no good theory to explain. In the 1990s, before the supernova data came in, most physicists thought dark energy did not exist. The standard model of cosmology had no place for it. Then, the data forced everyone to add it. Imagine building a puzzle, placing every piece you have, and realizing at the end that the puzzle is 70% empty space that you forgot to account for. That is where cosmology stood in 1999, and in many ways, that is where it still stands today. Scientists have proposed mechanisms, they have built models, they have argued over equations. But the fundamental question, what is dark energy actually made of, or whether it is even a thing at all versus a property of space itself, remains open, completely open, Nobel Prize level open. And here is where the story loops back to something old, because the strangest part of dark energy is that someone almost predicted it a century ago, and then he took it back. And now it turns out he might have been right the first time. That person was Albert Einstein, and what he wrote into his equations, then crossed out in embarrassment, might be the most important term in the history of physics. In 1917, Albert Einstein had a problem. He had just finished his general theory of relativity, which described how gravity worked across the entire universe. But when he applied his equations to the universe as a whole, they gave him a result that seemed obviously wrong. His equations said the universe had to be either expanding or contracting. It could not stand still. Einstein thought that was absurd. Everyone in 1917 thought the universe was static, eternal, unchanging. The idea that it was moving at all seemed ridiculous. So Einstein did something unusual. He added a term to his equation, a fudge factor. He called it the cosmological constant. It represented a kind of outward pressure built into space itself, strong enough to balance gravity and keep the universe from collapsing. The universe stayed still because gravity pulling inward and the cosmological constant pushing outward cancelled each other out. Problem solved. Einstein moved on. Then, in 1929, Edwin Hubble showed that galaxies were moving away from us. The universe was expanding. Einstein's equations had been right the first time. The universe was moving. His cosmological constant had been unnecessary. Einstein called it the biggest blunder of his career and removed it from his work. For decades, The cosmological constant was considered a historical footnote, a mistake made by a genius, a cautionary tale about forcing data to fit expectations. Then Perlmutter's team found their dimmer-than-expected supernovae, and suddenly everyone needed a force to explain why the universe was accelerating. And when physicists reached back into Einstein's abandoned equations, they found that the cosmological constant fit perfectly. Mathematically, adding the cosmological constant back into Einstein's general relativity explained the accelerating expansion exactly. The constant described a pressure built into the fabric of space itself, pushing outward, growing with the universe. It matched every observation. Einstein had invented the thing to fix a mistake, then thrown it away, and 70 years later it came back as the best explanation for the biggest discovery in modern cosmology. The blunder was right, just for the wrong reasons, at the wrong time. Physicists now use the cosmological constant as the leading model for dark energy. They call it lambda, the Greek letter Einstein used in his original equation. The current standard model of cosmology is often called lambda CDM, where lambda stands for the cosmological constant and CDM stands for cold, dark matter. The entire framework of modern cosmology rests on a term that Einstein crossed out in embarrassment. But here is where the story turns uncomfortable again. Because while the cosmological constant fits the observations beautifully, nobody knows what it actually is. The math works. The physical explanation does not exist. We can put lambda in the equation. We cannot explain why space would have this built-in outward pressure, where it comes from, or why it has the exact value it has. And that value is where things get genuinely disturbing, because the value of the cosmological constant is so precisely set that any slight change would have made our universe impossible. Imagine a dial. This dial controls one specific property of the universe: how strong dark energy is, how hard it pushes outward against gravity. Turn it up slightly, and galaxies never form. Turn it down slightly, and the universe collapses before stars ever ignite. The window where the dial can sit and allow a universe like ours to exist is incomprehensibly narrow. Physicists calculated what value dark energy, or the cosmological constant, needs to have for our universe to work. Then they calculated what value quantum physics predicts it should have. The predicted value is 10 raised to the power of 120 times larger than the actual value. To make that concrete, imagine trying to guess the distance from Earth to the edge of the observable universe in inches. Then imagine being off by a factor equal to the number of atoms in a trillion galaxies. That is the scale of the mismatch between what quantum physics predicts for dark energy and what we actually measure. This mismatch is called the vacuum catastrophe. It is widely considered the worst numerical disagreement in the history of science. Two of our best and most tested theories, general relativity and quantum mechanics, predict values for dark energy that disagree with each other by a number so extreme that it defies any known method of reconciliation. And yet, dark energy has exactly the value it needs to have for stars, planets, galaxies, and life to exist. There are two ways to react to this. One reaction: something about our physics is deeply wrong, probably in quantum mechanics, and once we fix it, the prediction will match the reality. The other reaction: the value is what it is because in a universe with a different value, nobody would be here to measure it. That second reaction has a name, and it leads into one of the most controversial ideas in all of physics. But before we get there is a crisis happening right now in the measurement of dark energy that most people outside of cosmology have never heard of. Because the Nobel Prize settled the fact of dark energy, but it left behind a ticking problem. Two completely different methods of measuring the same thing are giving two completely different answers, and the gap between them has been growing for years. Scientists have a name for this growing problem. They call it the Hubble tension, and it is threatening to do to modern cosmology exactly what the supernova data did to the old model. Two different groups of scientists set out to measure the same number. That number is the Hubble constant, named after Edwin Hubble. It describes how fast the universe is expanding right now. Measuring it is one of the most important tasks in modern cosmology. It tells us the universe's age, its size, and how dark energy is behaving. The first group looked at the cosmic microwave background. This is the faint glow of radiation left over from roughly 400,000 years after the Big Bang, when the universe first cooled enough for light to travel freely. It is the oldest light in the universe. Using this light and the standard model of cosmology, scientists can calculate what the Hubble constant should be today. Their answer: the universe is expanding at about 67 kilometers per second per megaparsec. For every 3.25 million light-years of distance, galaxies move apart by 67 kilometers every second. The second group used a different method. They built what astronomers call a distance ladder. They measured nearby stars whose distances they knew precisely. Then they used those to calibrate the distances to farther stars. Then farther still, all the way out to supernovae in distant galaxies. This method gives a direct, local measurement of the expansion rate today. Their answer: 73 kilometers per second per megaparsec. Those two numbers should be identical. They are measuring the same universe. The gap between 67 and 73 might sound small. In cosmology, it is enormous. It is a 9% difference between two measurements that should agree to a fraction of a percent. For years, physicists assumed one of the teams was making a subtle error. Better data would fix it. More precise instruments would close the gap. But as measurement techniques improved, the gap held, and then it grew slightly wider. Both measurements are now precise enough that the disagreement cannot be blamed on instrument error. The probability that both teams are simply measuring the same thing and getting different answers by chance is less than 1 in a million. Something real is causing the discrepancy. The most unsettling possibility is that the standard model of cosmology is missing something. Some piece of physics that was present in the early universe and changed the expansion history in a way nobody accounted for. Some new particle, some new behavior of dark energy, some unknown interaction that leaves a fingerprint in one measurement but not the other. If the Hubble tension is real, and the data increasingly says it is, then the model built on the Nobel Prize-winning discovery is already incomplete. The foundation has a crack, and nobody agrees on how to fix it. But the Hubble tension is just one crack, because recently, a telescope launched into the cold dark beyond Earth's atmosphere began sending back images of the early universe, and what it saw contradicted the model in an entirely different way. 13.8 billion years ago, the universe was a wall of fire. Everything everywhere was unimaginably hot, compressed, and glowing. Particles collided so constantly that light could not travel more than a tiny distance before being absorbed and re-emitted. The entire universe was opaque, like being inside a sun with no surface to escape through. Then, about 400,000 years after the Big Bang, the universe cooled just enough for the first atoms to form, electrons attached to protons. Suddenly, there was far less to block light. For the first time, photons could travel in straight lines across space. The universe became transparent. All that light, released in one cosmic exhale, is still traveling today. It has been flying through space for 13.4 billion years. By now, the expansion of the universe has stretched it so far that it has shifted completely out of visible light and into microwave radiation. It surrounds us on all sides. You can detect it with the right antenna. It is the faint background hiss that early television sets sometimes picked up between channels. Cosmologists call it the cosmic microwave background. It is a snapshot of the universe at its earliest visible moment, a baby photo of everything that ever existed. Scientists have mapped this ancient light with extraordinary precision, and buried in its patterns are the seeds of every structure in the universe. Every tiny ripple in that early glow became, over billions of years, the clusters and filaments of galaxies we see today. Using those patterns and the standard model of cosmology, scientists calculated where galaxies should be and how big they should have grown by now. The model makes specific, testable predictions about galaxy sizes, galaxy counts and how quickly structures formed. Then the James Webb Space Telescope began looking at the early universe, and the galaxies it found were wrong, too big, too massive, too developed. Galaxies that, according to the standard model, should have been small, young, and still forming, were already as large as the Milky Way, fully structured, shining with billions of stars, hundreds of millions of years after the Big Bang. Where the model predicted scattered dust and proto-galaxies, Webb found sprawling cities of stars. This does not automatically mean the model is broken. There are possible explanations. Maybe star formation in the early universe was far more efficient than models assumed. Maybe dark matter behaved differently then. Maybe there are measurement uncertainties in how we estimate the age of these galaxies. But the pattern is concerning. The cosmic microwave background disagrees with local expansion measurements. Webb disagrees with structure formation predictions. Two separate cracks pointing to the same foundation. And now a third problem is building. One that does not just threaten the model, one that threatens the very stability of dark energy itself. For 25 years, physicists assumed dark energy was constant. The cosmological constant that Einstein invented and then discarded has a fixed value. Every cubic inch of space has the same amount of it, now and forever. That assumption is baked into the name, constant. It does not change. It does not evolve. It sits in the equations like a fixed dial, unchanging across 13 billion years of cosmic history. That assumption just took a serious hit. In 2024, a research collaboration called the Dark Energy Spectroscopic Instrument released results from the largest ever map of the universe's structure. This instrument, mounted on a telescope in Arizona, used light from over 6 million galaxies to trace how the universe's expansion has changed over time. They were not just measuring the expansion rate today, they were measuring it across a wide span of cosmic history, going back billions of years, looking for any signs that dark energy had shifted. They found a hint, a pattern in the data suggesting that dark energy might be weaker today than it was in the past. Specifically, it appeared strongest around 5 billion years ago and may have been fading slightly since then. This result is not definitive. Scientists put it at roughly 2 sigma significance, which means there is about a 1 in 20 chance the pattern appeared by random chance. That is interesting, but not yet a confirmed discovery. Physics demands 5 sigma before calling something real. But here is why even a hint matters enormously. If dark energy changes over time, then the cosmological constant is wrong, not slightly wrong, fundamentally wrong. And if the cosmological constant is wrong, then every prediction made using it, including the fate of the universe, needs to be rebuilt from the ground up. A changing dark energy is not a small adjustment. It is a different universe. A universe where the force driving everything apart has a history, an origin, and possibly a future where it weakens or strengthens in ways nobody has calculated yet. The technical term for this possibility is that dark energy is not a constant but a field, a dynamic thing that evolves, shifts, and responds to the universe around it. Some physicists have been arguing for this possibility for decades. The cosmological constant always seemed too convenient, too static, too simple. A universe this complex, they argued, deserved a more complex explanation. If those physicists are right, the universe's future is not settled. The rate at which everything accelerates apart could be speeding up, slowing down, or even reversing, and the end of everything, which cosmology thought it had roughly mapped out, is wide open again. There are 3 main scenarios for how the universe ends, and the one that wins depends entirely on what dark energy turns out to be. Every story has an ending. The universe has 3 candidates. Which one happens depends on a single question. What does dark energy do next? The first ending is called the Big Freeze. In this scenario, dark energy stays roughly constant. The universe keeps expanding at a steady rate. Galaxies drift apart. Over hundreds of billions of years, star formation slows as gas clouds are stretched too thin to collapse. The last stars burn out. Black holes evaporate over unimaginably long timescales through a slow process called Hawking radiation. Eventually, the universe reaches a state of maximum cold and maximum disorder. Nothing moves, nothing burns, nothing happens. Ever again. This is the most widely accepted scenario given current data. It is also, in a quiet way, the most disturbing. No dramatic collapse, no explosion, just an infinite, silent, cold darkness, where the laws of physics continue operating on a universe with nothing left to operate on. The second ending requires dark energy to weaken over time. If the energy driving expansion gradually loses strength, gravity could eventually win. Expansion slows, halts, reverses. Galaxies fall toward each other. Galaxy clusters merge, then individual galaxies, then solar systems, then planets fall into stars, then stars into black holes, then black holes into each other. Everything collapses into a single point of infinite density, the Big Crunch. The universe ends the way it began, in a singularity of unimaginable compression. Some physicists find this ending almost elegant, creation and destruction as two sides of the same event. Others point out that the current data makes this the least likely of the three. Dark energy shows no sign of weakening, but the 2024 data hint that it might not be constant, which keeps this door slightly open. The third ending is the strangest. It requires dark energy to grow stronger over time. If it does, the consequences escalate from dramatic to violent to total. First, the expansion tears galaxy clusters apart. Then, individual galaxies shred. Then solar systems come apart as the force grows too strong for gravity to hold. Then planets break apart. Then the force reaches down to atomic scales. Eventually, it overpowers the electromagnetic force holding atoms together. Matter itself comes apart. Every nucleus, every proton, every electron tears free from every other. Every structure in the universe, from superclusters to hydrogen atoms, disintegrates in a final event called the Big Rip. In this scenario, the universe does not cool or collapse. It detonates. And the detonation happens at every scale, simultaneously, everywhere at once. The timing of the Big Rip, if dark energy is growing, is estimated at roughly 22 billion years from now. All three endings are currently on the table. The fate of everything depends on a force we still cannot directly detect, fully measure, or theoretically explain. And the theories built to explain it get stranger the deeper you go. 22 billion years from now, the universe ends in 10 minutes. That sentence needs some unpacking. The Big Rip is the most violent of the three possible endings, and its final moments are among the most dramatic sequences in all of cosmology. For most of those 22 billion years, the Big Rip looks almost identical to the Big Freeze. Galaxies drift apart, the sky empties, stars burn out one by one. Life, if any exists anywhere, watches the cosmos grow quieter and darker. But then the math turns. About 1 billion years before the end, galaxies begin tearing apart from the inside. The expansion force finally overcomes the gravity holding them together. Stars that have circled galactic centers for billions of years suddenly fly outward into the void. The Milky Way, if it still exists in some form, simply comes apart. Every star leaves every other star forever. 60 million years before the end, solar systems break apart. Planets that have orbited stars for billions of years drift away. The gravitational bond between a star and its planets, the force that held our solar system together since before Earth existed, snaps like a stretched rubber band. Every planet in every solar system, in whatever remains of the universe, goes dark and cold as it loses its star. 3 months before the end, the expansion force reaches the scale of individual planets. Earth, if it survived everything else, would be torn apart. The rock and iron of the planet's interior would separate. Oceans, mountains, and continents would fly outward into space. 30 minutes before the end, atoms lose their electrons. The electromagnetic force that holds atomic structure together gets overpowered. Every atom in the universe becomes a naked nucleus surrounded by loose electrons that can never reconnect. Then, in the final moments, the strong nuclear force fails. Protons and neutrons split apart into their component quarks. Every nucleus in the universe disintegrates simultaneously. Matter, in any form recognizable by physics, ceases to exist. The universe ends in a state of pure, disconnected particles, with nowhere to go and nothing to connect to. This scenario depends entirely on dark energy being a form physicists call phantom energy, a type that grows in strength as the universe expands, with no upper limit. Whether phantom energy is real, whether dark energy is even capable of growing stronger, remains unknown. The 2024 data hint at dark energy changing, but they do not yet point clearly toward the Big Rip. What makes the Big Rip genuinely unsettling beyond the violence is the timing. The final shredding of everything happens in minutes. After 22 billion years of gradual drift, the last chapter of the universe takes 10 minutes to finish, quiet for billions of years. Then everything, everywhere, all at once. But phantom energy is only one candidate for what dark energy might be. Some physicists argue for something else entirely, something that does not just change over time but actively evolves like a living field woven through the fabric of space. And that idea has a name that sounds almost gentle compared to what it implies. What if dark energy is alive? Not alive in a biological sense, alive in the sense that it moves, changes, evolves, and responds to the universe around it the way weather responds to heat and pressure. What if the force driving everything apart is less like a fixed wall and more like a slow-moving tide? This idea has a name, quintessence, and it is one of the most serious alternatives to the cosmological constant that physicists have proposed. Quintessence comes from ancient Greek philosophy. The original idea was a fifth fundamental substance beyond earth, water, fire, and air. Medieval thinkers used it to describe the material that made up the stars and heavens. Modern physicists borrowed the word for a form of dark energy that behaves like a dynamic field, spread across all of space but changing in strength as the universe evolves. The cosmological constant is simple, one value, fixed forever. Quintessence is complicated. It has a value that can shift. In some models, it was stronger in the past and has been weakening. In others, it was weaker and is building towards something. In some versions, it oscillates, strengthening and weakening over billions of years in a slow cosmic pulse. Here is why physicists take quintessence seriously instead of dismissing it as speculation. The cosmological constant faces a brutal mathematical problem that quintessence sidesteps. With a fixed constant, you have to explain why it has exactly the value it has. No more, no less, permanent, forever. Quintessence can potentially evolve toward its current value naturally over cosmic time, the way a ball rolling down a hill settles into a valley. The value we measure today would be a moment in a longer process, not a permanent fixed number demanding explanation. The 2024 data from the Dark Energy Spectroscopic Instrument, with its hint that dark energy may have weakened since 5 billion years ago, fits some quintessence models better than it fits the cosmological constant. If that data strengthens over the next few years, quintessence moves from interesting idea to frontrunner. The practical stakes are enormous. If dark energy is quintessence, and it has been weakening, the Big Rip becomes impossible. A weakening dark energy eventually loses to gravity, opening the door toward the Big Crunch instead. If quintessence is cycling, the universe's fate could oscillate between expansion and contraction over timescales we can barely conceptualize. Every model of the universe's future depends on which of these dark energy descriptions is correct, and every one of them is still in play. But there is a deeper problem lurking under all of this. Something that does not just challenge our model of dark energy, something that challenges whether our two most successful theories of physics can ever be made to agree. Quantum mechanics is the most precisely tested theory in the history of science. It predicts the behavior of electrons so accurately that the agreement between theory and experiment is equivalent to measuring the distance from New York to Los Angeles and getting it right to within the width of a human hair. Quantum mechanics works. Nobody seriously doubts it. General relativity is the other pillar of modern physics. It describes gravity and the large-scale structure of space and time with extraordinary accuracy. It predicted black holes before anyone found one. It predicted gravitational waves a century before we detected them. General relativity works too, so when both theories make a prediction about the same thing, you expect them to agree. They do not have to match perfectly. Physics has many examples where different theories give slightly different answers that need reconciling, but you would expect them to be in the same neighborhood. When physicists calculated the predicted value of dark energy using quantum mechanics and then compared it to the value actually measured from the supernova data and the cosmic microwave background, the two numbers were separated by a factor of 10 raised to the power of 120. That number is larger than the number of atoms in the observable universe by a lot. It is so large that it does not correspond to anything physical. It is simply a measure of how completely the prediction fails. This is the vacuum catastrophe. Quantum mechanics predicts that empty space should be seething with energy from virtual particles that pop in and out of existence constantly. That energy should contribute to the cosmological constant. When physicists add it all up, they get a value for dark energy that would make the universe expand so violently, so instantly, that no atom, no star, no galaxy, no particle could ever form. The universe would tear itself apart in the first fraction of a second. That obviously did not happen, which means either quantum mechanics is wrong about virtual particles, which seems unlikely given how well it predicts everything else, or something is cancelling out almost all of that energy with precision that defies any known mechanism, or the two theories simply cannot coexist, and one of them will eventually need to be replaced. Physicists have been trying to solve the vacuum catastrophe for over half a century. Nobody has cracked it. Every proposed solution either fails mathematically or creates new problems as severe as the one it fixes. The mismatch does not just mean our dark energy theory is incomplete. It means our most fundamental theories of how reality works are incompatible at a deep level. And the universe's accelerating expansion, measured by a team of exhausted astronomers watching distant stars explode, is the proof. Something above all of this needs to give, and the theories fighting to fill the gap push physics into territory that sounds more like science fiction than science. String theory was supposed to be the answer to everything. The idea is that all fundamental particles, electrons, quarks, photons, everything physical, are at the deepest level tiny vibrating strings of energy. Different vibration patterns create different particles. The forces of nature arise from the way strings interact. If correct, string theory would unify quantum mechanics and general relativity into one framework. The biggest problem in physics solved. String theory makes a specific prediction about the universe we live in. To be mathematically consistent, it requires the universe to have 10 spatial dimensions, not 3. The extra dimensions are thought to be curled up so small that no experiment has ever detected them. But here is where it gets strange. The mathematics of string theory does not produce one unique universe. It produces an enormous number of possible universes, each with different physical laws, different particle masses, different values for the cosmological constant, different strengths for every fundamental force. How many possible universes? Roughly 10 raised to the power of 500. That number has 500 zeros. It is so large that writing it out would take more space than exists in the observable universe. This collection of possible universes is called the string landscape. Each universe in the landscape is a pocket with its own rules. Most of them have no resemblance to ours. Most have values of the cosmological constant that are far too large for structure to form. Many have physics so exotic that atoms cannot exist. Only an incredibly tiny fraction of the landscape produces universes anything like the one we live in. String theory does not tell us which universe we live in. It says we live in one of them, and our universe's physical laws, including the specific tiny value of dark energy, are just the rules of our particular pocket. This does not sit well with many physicists. Science is supposed to make predictions you can test. If your theory produces 10 to the power of 500 possible universes and cannot tell you which one you are in, some argue it is not a scientific theory at all. It is a mathematical object that happens to contain our universe somewhere inside it, but offers no way to find it. Others argue that the landscape, as uncomfortable as it feels, might simply be reality. The universe does not owe us simplicity. If the vacuum catastrophe cannot be solved by finding a unique, correct value for the cosmological constant, maybe the only answer is that the value is one of countless possible values, and we live here because here is where the value allows us to exist. That argument has a name that generates fierce debate every time it is raised. Why does dark energy have exactly the value it has? That question has haunted physics since the supernova data came in. The vacuum catastrophe shows that quantum mechanics predicts a value 10 to the power of 120 times too large. String theory offers 10 to the power of 500 possible universes with different values, and the actual measured value sits in an absurdly narrow range where structure, stars, galaxies, and life can exist. Some physicists have an answer. They call it the anthropic principle. The logic goes like this. Suppose the string landscape is real. Suppose there are an enormous number of universes with different values for the cosmological constant. In the vast majority of those universes, dark energy is either far too strong, tearing space apart before anything forms, or dark energy is strong in the opposite direction, allowing gravity to collapse everything before stars ever ignite. Those universes exist. They are simply empty of any observer to notice them. The universes with a cosmological constant in the tiny range that allows galaxies, stars, planets, and life will, by definition, contain observers. Those observers will measure the cosmological constant and find it has a value compatible with their existence. They could not measure it and find otherwise, because if it were otherwise, they would not exist. We measure the value we measure because we can only exist in a universe where that value works. The anthropic principle says the precise tuning of dark energy is not a mystery requiring a physical explanation. It is a selection effect. We selected ourselves into a universe where the numbers worked. In 2000 and the year 2000, physicist Steven Weinberg used a version of this argument to predict the value of the cosmological constant before it was measured. He reasoned that it had to be small enough to allow galaxies to form, but could be anything within that range. His prediction matched the observed value roughly. That success gave the anthropic argument more credibility than most physicists were comfortable with. Many physicists hate this answer, not because it is logically wrong, because it feels like quitting. If the answer to why dark energy has this value is simply because we would not be here to ask otherwise, then physics has reached a wall. There is no deeper mechanism to find, no equation that explains the tuning. The universe is what it is because the alternatives are empty. Others argue that this discomfort is not a scientific objection. Physics does not have to feel satisfying. If the landscape is real and the anthropic principle explains the cosmological constant, that is the answer, whether we like it or not. The debate between these camps is one of the most raw and honest arguments in modern science. It is a fight about what physics is allowed to accept as an explanation, and it is nowhere near settled. But while that argument continues, a completely different set of scientists took a different approach. Instead of explaining dark energy, they asked whether it exists at all. And their answer pointed to something even more fundamental being wrong. What if dark energy does not exist? That question sounds like giving up. But for a growing number of physicists, it is the most honest response to a force that has never been directly detected, never been explained, and sits at the center of the worst mathematical disagreement in the history of science. Their argument goes like this: we invented dark energy to explain why the universe is accelerating, but we assumed something along the way, that Einstein's equations for gravity work perfectly at cosmic scales. We tested general relativity on planets, on light bending around stars, on GPS satellites. It passes every test in those settings, but we have never truly tested it at the scale of the full universe, across billions of light years, over billions of years of time. What if gravity behaves differently at those scales? What if the equations we are using are simply the close-range approximation of a deeper theory, one that changes its behavior when applied across the full width of the cosmos? In that case, there would be no need for dark energy. The acceleration would be a natural consequence of gravity working differently at extreme distances, something the current equations cannot account for. These modified gravity theories come in several flavors. One of the most discussed is called modified Newtonian dynamics, originally proposed to explain galaxy rotation curves without dark matter. Later versions attempt to explain cosmic acceleration without dark energy. Another approach changes the mathematical structure of Einstein's field equations at large scales, adding terms that become significant only when distances reach hundreds of millions of light years. None of these theories has yet matched the full range of observations that the cosmological constant model handles. The standard model with dark energy and dark matter reproduces an enormous variety of data: the cosmic microwave background patterns, the large-scale structure of the universe, galaxy clustering statistics, supernova brightness measurements. Modified gravity theories often explain one or two of these well, then struggle with the others. But here is the important point. Every time a new crack appears in the standard model, whether the Hubble tension, the Webb telescope galaxy sizes, or the 2024 Dark Energy Survey hints, modified gravity theories gain a little more room to breathe. If the standard model has problems, alternatives deserve a harder look. The deeper motivation behind modified gravity is philosophical as much as scientific. Dark energy is a placeholder. It is a label for ignorance. Putting a term in an equation and calling it solved is not the same as understanding something. Modified gravity at least proposes a mechanism, a change in how the universe's most familiar force operates when pushed to its limits. Whether that mechanism is right remains to be seen. But the fact that serious physicists are building careers on the possibility that gravity itself is the thing we got wrong tells you everything about the current state of cosmology. The ground is unstable, every assumption is being questioned, and the next telescope to go online may be the one that finally forces a decision. The James Webb Space Telescope cost $10 billion, took 30 years to build, and folded itself into a rocket like origami before unfolding in cold space, 1,000,000 miles from Earth. It was designed to see the first galaxies, the ones that formed in the universe's first few 100 million years, when everything was young and chaotic and still assembling itself from the wreckage of the Big Bang. Scientists expected to find small, irregular, chaotic proto-galaxies, blobs of gas and young stars just beginning to organize themselves. What they found instead stopped cosmologists cold. Fully formed galaxies, massive ones, structured ones, with spiral arms, dense cores, and populations of stars billions of years old by the time the universe itself was only a few 100 million years old. Galaxies that, according to the standard model, had no business being that large, that organized, that early. One galaxy, spotted by Webb, existed when the universe was only 300 million years old. It already contained roughly as many stars as our Milky Way does today. The Milky Way took over 10 billion years to build that population. This galaxy apparently did it in a fraction of the time. The standard model of cosmology predicts how quickly matter can clump together under gravity. It has a speed limit set by the physics of dark matter and ordinary matter interacting under the constraints of the early universe. Galaxies cannot grow faster than gravity and gas physics allow. Webb's early galaxies appear to have ignored that speed limit. There are several responses to this. 1. The mass estimates for these early galaxies could be wrong. Measuring a galaxy's mass from its light involves assumptions about its stars. If those assumptions are slightly off, the galaxies might be smaller than they appear. Researchers are refining the measurements. 2. Star formation in the early universe might have been dramatically more efficient than models predict. If the first generation of stars formed with very little wasted material, galaxies could have built up faster than current models allow. Some physicists are exploring this possibility seriously. 3. Something is wrong with the model itself. Dark matter might have behaved differently in the early universe, clumping faster or more efficiently than simulations predict. Or dark energy might have played a different role in the early universe than it does today, another hint that it is changing over time. 4. There is new physics. Something operating in the early universe that the standard model does not include, that accelerated structure formation in ways nobody predicted. Each of these explanations is being tested right now. Webb is still returning data. The picture is not yet clear, but the pattern is hard to ignore. Multiple independent observations, galaxy sizes, expansion rate measurements, structure formation histories, are all pointing at the same model and finding it slightly wrong in the same direction. Every crack points the same way. And the next generation of surveys is about to expose the full width of the fracture. In the Arizona desert, a telescope has been staring at the sky every clear night for years. It is not the largest telescope ever built. It is not the most sensitive, but it is equipped with 5,000 optical fibers, each one pointed at a different galaxy simultaneously, capturing the light from 5,000 galaxies in a single night. Over the course of its survey, it will measure the precise positions and distances of roughly 40 million galaxies, stretching across 11 billion years of cosmic history. This is the Dark Energy Spectroscopic Instrument, and the map it is building is the most detailed three-dimensional picture of the universe ever attempted. The goal is to trace how the universe's large-scale structure has changed over time. Galaxies do not spread out randomly. They form along filaments and sheets, clustering into walls and nodes with enormous empty voids between them. The exact shape of that structure at different points in history carries information about how dark energy has behaved, how gravity has competed with expansion, and whether the standard model correctly predicts the universe's evolution. By comparing the structure at different cosmic epochs, scientists can essentially watch dark energy work in slow motion across billions of years. If dark energy is constant, the structure evolves in one specific way. If dark energy is changing, the structure evolves differently. The differences are subtle, but with 40 million galaxies, even subtle differences become statistically visible. The 2024 results, the ones that hinted dark energy may have weakened since 5 billion years ago, came from the first year of data. Only about 10 million galaxies measured, roughly 1/4 of the full survey complete. When the full dataset arrives, the statistical power will be 4 times greater. Hints at 2 sigma significance could rise to confirmed discoveries. The gap between the cosmological constant and a dynamic dark energy could become visible enough to force a clear answer. This survey will not work alone. It runs alongside the Euclid Space Telescope, launched by the European Space Agency, which is mapping galaxies from orbit with a wide-angle camera covering 1/3 of the entire sky. Euclid and the Dark Energy Spectroscopic Instrument measure different things in different ways. When their results combine, the overlap creates cross-checks that make any discovery far harder to dismiss as instrument error. Add the Vera Rubin Observatory in Chile, which begins its 10-year sky survey and will photograph the entire southern sky every few nights, catching supernovae in real time across billions of light years. Three major instruments, each attacking the dark energy problem from a different angle, all coming online within a few years of each other. The next decade of cosmology will generate more data about the universe's expansion history than all previous decades combined. If dark energy is changing, this wave of surveys will prove it. If modified gravity is real, the structure maps will show signatures that no dark energy model can reproduce. If the standard model holds, every measurement will converge on the same answer, and the Hubble tension will need a different explanation. The answer is coming, but the answer might open a door into something even harder to explain. Here is an assumption baked into almost everything in modern cosmology. The universe is flat, not flat like a table, flat in the mathematical sense. It means that the geometry of space follows the rules you learned in school. Parallel lines stay parallel forever. The angles of a triangle add up to 180 degrees. The shortest distance between 2 points is a straight line. This assumption has strong observational support. The patterns in the cosmic microwave background match a flat universe with extraordinary precision. The standard model assumes flatness and reproduces dozens of independent observations correctly. But flatness is not proven. It is measured to be very close to flat, within a small margin of error. And some physicists argue that small deviation from perfect flatness, if it is real and not just measurement noise, could change the story of dark energy entirely. A universe with positive curvature, curved like the surface of a sphere, behaves differently than a flat one. Light curves. Parallel lines eventually meet. Triangles have angles that add to more than 180 degrees. In such a universe, the apparent acceleration of the expansion could be partly or entirely a geometric effect, rather than a real force pushing galaxies apart. The argument runs like this. If we assume the universe is flat and it is actually slightly curved, then our distance measurements are wrong. The supernovae that appear dimmer than expected could be dimmer because they are actually in a different geometric location than our flat universe equations predict, not because something is accelerating the expansion. Our measuring stick would be miscalibrated from the start. A team of researchers published work in 2020 suggesting that the cosmic microwave background data actually prefer a slightly curved universe over a flat one. The analysis was contested. Other teams argued the preference was marginal and model dependent. The debate has continued without resolution. If the universe is curved even slightly, almost every major conclusion of modern cosmology requires revision. The age of the universe, the size of the observable universe, the amount of dark energy needed to explain observations, the predicted structure of galaxies across cosmic time. This is one reason physicists track the curvature question so carefully alongside the dark energy measurements. A change in one changes the interpretation of the other. The surveys coming online in the next decade will measure the universe's geometry with 10 times more precision than anything done before. But geometry is not the strangest possibility waiting in the data, because some physicists argue the problem runs even deeper. They argue that the fundamental constants of nature, the things we assume are fixed forever, might not be fixed at all. The speed of light is 300 million meters per second, always, everywhere, in every direction. That constancy is one of the absolute foundations of modern physics. Einstein built his entire theory of relativity on it. Remove it and the equations collapse. So, what happens when observations hint that the speed of light, or other fundamental constants, might have been different in the early universe? This is a deeply controversial area of physics. The mainstream view is firm. Fundamental constants are constant. They do not change over time or across space. The evidence for this comes from precise measurements of atomic spectra from distant quasars. The light from these ancient, powerful objects carries fingerprints of atoms that are billions of years old. If the fine structure constant, a number that controls how light interacts with electrons, had been different back then, those atomic fingerprints would look different than they do in laboratories today. For decades, they matched. Then, a team of researchers analyzing quasar spectra found a tiny discrepancy, a hint that the fine structure constant might be slightly different in one direction across the sky compared to another. The effect was small, it was contested. Other teams did not find it in their data, but the implications, if true, would be seismic. If fundamental constants vary across space, then the universe has a kind of directional structure, a preferred orientation, that the standard model says should not exist. Cosmology assumes the universe looks the same in every direction at large scales. A universe where constants differ depending on which way you look is a fundamentally different kind of universe. And here is the connection to dark energy. Several theoretical frameworks that propose varying constants also modify the behavior of dark energy. A universe where the speed of light has shifted slightly over cosmic time, or where the strength of gravity has a small time dependence, would expand differently than the standard model predicts. The Hubble tension, the gap between the two measurements of the expansion rate, might be a symptom of exactly this kind of variation. The physicists pursuing varying constants are a minority. The mainstream holds that the evidence is not strong enough, but minority positions in physics have a history of becoming mainstream when the data finally catches up. If constants vary, then nothing about the universe can be taken as truly fixed. Every equation becomes an approximation valid only in a specific time and place. Physics becomes local, not universal, and the rules that a Nobel Prize winner exposed as broken might be just the first of many to fall. Walk into any university library and pull a cosmology textbook off the shelf. It will tell you the universe is 13.8 billion years old. It will tell you the universe is made of roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. It will tell you the expansion of the universe is accelerating, confirmed by a Nobel Prize. It will present this as settled science, the standard model of cosmology, a framework so well supported that it deserves its own name, Lambda CDM. What it probably will not tell you is that this model has at least 3 serious unresolved tensions that have grown stronger every year for the past decade. The Hubble tension sits at the center. 2 independent measurements of the universe's expansion rate disagree by 9%. Both are precise. Both are carefully checked. Neither shows a sign of giving way. This has been known since around 2013 and has grown steadily worse as instruments improved. A model with a 9% unexplained discrepancy in its central measurement is a model under stress. The sigma-8 tension is less famous but equally stubborn. It describes a mismatch between predictions and observations of how clumped together matter is in the universe today. The standard model, calibrated on the cosmic microwave background, predicts slightly more clumping than we observe in galaxy surveys. 2 different measurements of the same thing, giving 2 different answers, for reasons nobody has pinned down. And now the Webb telescope galaxies. Too big, too early, too structured for the standard model's timeline of galaxy formation. Each tension, taken alone, could be an error, a subtle bias in measurements, a wrong assumption somewhere in the analysis pipeline. Scientists have spent years hunting for those errors and have not found them. Taken together, the pattern becomes harder to dismiss. 3 independent tensions, all pulling in directions that suggest the standard model is slightly wrong in a consistent way, point towards something missing from the model. Some physics that was present in the early universe and changed the evolution in ways Lambda CDM does not account for. This is not a crisis in the sense of panic. Physics is not broken. Predictions still work for most purposes. Satellites still launch. Particle accelerators still find what they expect. The crisis is specific to cosmology, to our model of the universe's history and fate, and it is a productive crisis, one that is driving the next generation of experiments. But it matters for the public understanding of science that this is happening. The textbooks teach the standard model as if it is finished. The scientists building those textbooks know it is unfinished. The gap between what is taught and what is actively debated at the research frontier is wider in cosmology right now than it has been in decades. And the next discovery, the one that finally breaks the dam, might already be hiding in the data, 40 million galaxies will not be enough. The Dark Energy Spectroscopic Instrument is mapping 40 million. The Euclid telescope will map billions. The Vera Rubin Observatory will photograph the southern sky every few nights for a decade, building a time-lapse of the cosmos. These three instruments together will generate more raw cosmological data than all previous surveys combined. But the signal physicists are hunting is buried under layers of noise. Dark energy does not announce itself. It leaves fingerprints, subtle distortions in how galaxies cluster, in how fast structures grow, in tiny patterns in the cosmic microwave background that require vast statistical samples to resolve. Pulling that signal out of billions of data points requires not just more telescopes, but new mathematical tools built to handle data at a scale that was impossible a decade ago. This is where machine learning enters cosmology in a serious way. Neural networks trained on simulated universes can scan real galaxy surveys and identify patterns too subtle for traditional analysis. They can detect deviations from the standard model that would be invisible to human eyes reviewing the data directly. They can test thousands of alternative cosmological models against the data simultaneously. The risk is real. If the training data is built on the standard model, the network might fail to flag deviations from it. Scientists are working on training methods that expose networks to a wide range of alternative cosmologies, including modified gravity theories, quintessence models, and varying constant scenarios. The goal is a system that finds the universe's actual rules rather than confirming what researchers already believe. The combination of survey scale and analytical power means the next decade of cosmology will be unlike any that came before. Questions that have been debated for 25 years since the Nobel Prize-winning discovery may finally get hard answers. Is dark energy constant or changing? Is gravity modified at cosmic scales? Is the Hubble tension a measurement error or a sign of new physics? At least some of those questions will be answered by data that already exists, sitting in hard drives in universities around the world, waiting to be processed by the right algorithm. The universe has been encoding its secrets in the light of a billion galaxies. The tools to read that code are almost ready, and what the code says might rewrite the story from the beginning. General relativity and quantum mechanics are the two most successful scientific theories ever created. Together, they describe everything from the orbit of planets to the behavior of electrons inside a computer chip. Every technology built in the last 100 years depends on one or both of them. They have been tested to extraordinary precision and passed every test. They are also fundamentally incompatible. General relativity describes gravity as the curving of space-time by mass. Space and time bend. Objects follow those curves. The theory is smooth, continuous, and geometric. It works on large scales: planets, stars, galaxies, the universe itself. Quantum mechanics describes everything at the smallest scales as inherently probabilistic and discontinuous. Particles jump between states. Measurements affect outcomes. The universe, at the quantum level, is a fog of probabilities that only resolves when observed. It works on small scales: atoms, electrons, photons, the fundamental forces. When you try to apply quantum mechanics to gravity, the equations explode. You get infinities where you need finite numbers. The math breaks down in a way that cannot be fixed with the techniques that work elsewhere. This is not a minor technical issue. It is a fundamental incompatibility between two theories that both claim to describe reality. The search for a theory that unifies them, a theory of quantum gravity, is the central goal of theoretical physics. String theory is one attempt. Loop quantum gravity is another. Causal dynamical triangulation. Asymptotic safety. Twistor theory. There are dozens of serious proposals, none of which has produced a testable prediction that distinguishes it from competitors and been confirmed by experiment. Dark energy sits precisely at the intersection of this incompatibility. It operates at the largest possible scales, where general relativity is the right tool, but its origin may lie in quantum processes in empty space. where quantum mechanics is the right tool. The vacuum catastrophe, the mismatch between the quantum prediction for dark energy and its measured value, is a direct symptom of these two theories failing to work together. Solving dark energy may require solving the incompatibility between the two pillars of modern physics. That is a problem physicists have been working on for a century without producing an agreed-upon answer. Whatever comes next will be the biggest conceptual leap in physics since general relativity itself, and the clue that unlocks it might come from the most unexpected direction, not from a particle accelerator or a space telescope, but from a completely new way of thinking about what space itself is made of. Space feels like nothing. You reach your hand out into the air and feel no resistance. You look out a window and see emptiness between you and the sky. Space seems to be the absence of things, the container that holds matter and energy, the blank stage on which the universe performs. Modern physics disagrees with that description completely. Empty space, in quantum mechanics, is not empty. It is a seething, churning ocean of activity at scales far smaller than any atom. Virtual particles pop into existence and vanish in fractions of a second. Fields fluctuate. Energy appears and disappears in amounts that are real, measurable, and consequential. This quantum vacuum, the true nature of empty space, has observable effects. One of them, called the Casimir effect, has been measured in laboratories. Place two metal plates nanometers apart in a vacuum, and the quantum fluctuations between them differ from the fluctuations outside them. The plates are pushed together by this difference, pushed by nothing in a vacuum, because nothing in quantum mechanics is never truly empty. The energy of this quantum vacuum is what quantum mechanics predicts should drive the cosmological constant. And as we have seen, the prediction is catastrophically wrong. Either the quantum vacuum energy is almost completely cancelled by something unknown, leaving only a tiny residue that we call dark energy, or our understanding of the quantum vacuum is fundamentally mistaken. Some physicists are exploring a radical alternative. What if space itself is not fundamental? What if space, the container we assume everything sits inside, is actually an emergent property of something deeper? Something that does not have spatial extent in the way we think of it, but gives rise to the appearance of space at the scales we can observe? This idea appears in several approaches to quantum gravity. In one framework, space emerges from the quantum entanglement between regions of a deeper layer of reality. In another, space-time is woven from a network of quantum events connected by probability rather than geometry. In these pictures, the properties of empty space, including its energy content and the behavior of dark energy, would be determined by the structure of the underlying layer. If space is emergent, then asking why the cosmological constant has a specific value is like asking why the surface of a lake has a specific temperature. The answer lies not in the surface itself, but in the deeper molecular activity producing it. These ideas are speculative. None has made confirmed predictions, but they represent where the smartest people in physics go when they conclude that our current framework has run out of room to grow. The universe's most perplexing quantity, the energy of empty space, may only be explainable by reconceiving what space itself is. The first Nobel Prize for dark energy rewarded its discovery. The second one, if it comes, will reward its explanation. And the prize criteria for that explanation are steep. It would need to tell us what dark energy actually is, derive its value from first principles without fudging, explain why the vacuum catastrophe does not invalidate it, and make predictions that are then confirmed by observation. Ideally, it would also resolve the Hubble tension and explain the Webb telescope's early galaxies as a natural consequence. No current theory does all of this. Several do pieces of it. The most promising near-term target is a definitive measurement of whether dark energy is changing. The surveys coming online in this decade have the statistical power to push the 2024 hint from interesting to conclusive. If dark energy is confirmed to be dynamic, That rules out the cosmological constant and opens the field to quintessence and related models. Researchers working on those models would have a clear target: explain the specific way dark energy has changed over time, derive that behavior from a physical mechanism, and predict what it will do next. A confirmed detection of dark energy's nature, even without a full theoretical explanation, would represent a transformation of the field comparable to what Perlmutter, Schmidt, and Rees achieved in 1998. It would shift cosmology from cataloging a mystery to measuring a mechanism. The more dramatic possibility is a direct detection of the quantum vacuum energy in a way that finally connects the quantum prediction to the observed value. If an experiment could measure the structure of the quantum vacuum with enough precision to find where the cancellation occurs, the mechanism behind the cosmological constant might become visible. Several experiments in quantum optics and precision measurement are pushing toward this goal. Then there is the unification scenario. If string theory or another quantum gravity framework finally produces a testable prediction, and that prediction is confirmed, the Nobel Prize would dwarf anything that came before it. Unifying the two pillars of physics while explaining dark energy as a consequence of that unification would be the single greatest scientific achievement since Newton described gravity with mathematics. Each of these paths is being actively pursued. Each would change what we know about the universe more profoundly than anything in a generation, and each begins with the same observation: a set of distant exploding stars that came out dimmer than expected, measured by exhausted teams of astronomers who assumed they had made a mistake. When cosmologists say the universe is 13.8 billion years old, they are using the Standard Model to calculate backward from what we observe today. They know the current expansion rate. They know the amount of matter and dark energy in the universe. They run the equations in reverse and ask, how long ago would everything have been compressed into a single point? The answer is 13.8 billion years. But if the expansion rate is not what we think, because of the Hubble tension, then the age calculation changes. A higher expansion rate means the universe is younger than 13.8 billion years. A lower rate means it is older. The two measurements at the center of the Hubble tension give expansion rates that imply ages differing by over 1 billion years. That is a billion-year uncertainty in the age of everything that ever existed. It gets more complicated. The ages of the oldest stars in our galaxy can be estimated independently from their chemistry and brightness. Some of those stars appear to be very close to 13.8 billion years old. If the universe is actually younger than that estimate due to a higher expansion rate, then the universe contains stars that are older than the universe itself. That is obviously impossible, which means either the stellar age estimates are wrong, or the expansion rate is wrong, or the model connecting them is wrong. This is not a theoretical issue. It is an internal contradiction in the current model. The resolution will require revising at least one of these measurements, and revising any of them propagates through every cosmological calculation that depends on it. Everything built on the Standard Model, the predicted abundances of elements from the Big Bang, the structure of the cosmic microwave background, the expected number of galaxies at each epoch, the formation history of galaxy clusters, all of it carries the assumption that the expansion rate and the age are what the model says. If they are not, every one of those calculations needs to be redone. This is why the Hubble tension is taken seriously by researchers who might otherwise prefer not to contemplate a broken model. The stakes are not abstract. The foundations of cosmological history are only as solid as the measurements underneath them. And right now, the most important measurement has two answers. There is a boundary around you that you can never cross or even see past. It is called the cosmic event horizon. It exists because the universe is expanding so fast that light from beyond a certain distance will never reach you. The galaxies on the other side of that horizon are moving away faster than light can travel toward you. Their light is running in the right direction, but the space between you and them is growing faster than the light can cover it. That horizon sits roughly 46 billion light-years away in every direction. Everything inside that sphere is the observable universe. Everything outside is, for all practical and physical purposes, gone, unreachable, unknowable, forever. And because dark energy is accelerating the expansion, that horizon is effectively shrinking over time. Not shrinking in absolute size, but shrinking in terms of how much of the universe it includes. Galaxies that are borderline reachable today will cross the horizon in the future. Their light, currently just barely making it to us, will eventually stop arriving as expansion carries them over the edge. In 1 billion years, several galaxy clusters visible today will be gone from our sky. In 100 billion years, only the galaxies gravitationally bound to our local group will remain visible. The Milky Way, Andromeda, and a few dozen smaller galaxies will be surrounded by an empty sky. Every other galaxy, every other cluster, every other structure in the universe will have crossed the horizon. In 1 trillion years, the sky will be dark except for the glow of our own galaxy. Astronomers at that point, if any exist, will have no observational evidence that any other galaxy ever existed. The light will be gone, the evidence will be gone, the entire history of the universe outside our local group will be, from their perspective, as if it never happened. Dark energy is not just shaping the universe's future, it is erasing the universe's past from the perspective of any future observer. The more time passes, the less of the cosmos anyone inside it can ever know about. This means we are, right now, in the best era to study the universe that will ever exist. The sky has never been fuller and will never be again. Here is a thought that should stay with you. Every fact we know about the universe comes from light. We observe electromagnetic radiation, radio waves, infrared, visible light, ultraviolet, X-rays, gamma rays, plus gravitational waves, and cosmic ray particles. Every measurement, every photograph, every spectrum, every data point in the history of astronomy arrived here because something sent a signal, and that signal reached us. Dark energy guarantees that the number of signals we can ever receive is shrinking. Every year, more of the universe crosses the event horizon. Every year, more light that was theoretically on its way to us gets stretched and dimmed beyond detection. The total amount of information the universe can ever deliver to any observer inside it is finite, and we are spending it down. This creates a specific kind of philosophical and scientific unease. The rules of the universe, including the ones being broken or questioned right now, may be fundamentally unknowable to any observer within it. If the cosmological constant is what it is because we live in one pocket of a vast landscape of universes, we can never visit the others to confirm it. If dark energy varies across the history of the universe, the parts of that history now beyond our horizon are gone from our data forever. If the universe has a shape, a curvature, a structure at scales beyond what we can observe, we have no access to the evidence. Science operates on the assumption that the universe is knowable, that careful observation and rigorous mathematics can eventually reveal how reality works. Dark energy forces a harder question. Knowable from where? From inside a finite bubble of observable space, with a horizon that shrinks as you watch? Perlmutter and his team stared at dimmer than expected stars and found a rule broken. What they also found, though nobody quite said it this way at the time, was that the universe imposes limits on how much any observer inside it can ever learn. The accelerating expansion is simultaneously the most dramatic discovery of the last century and a kind of cosmic ceiling on what discovery can ever reach. The broken rule did not just change what we know, it changed what we can know. Right now, somewhere, a graduate student is staring at a graph that does not look right. Maybe it is a galaxy that is too big for its age in web data. Maybe it is a supernova that falls slightly outside the expected brightness curve. Maybe it is a tiny statistical anomaly in a dark energy survey that will resolve into noise or resolve into the discovery that changes everything. The people who will solve the dark energy problem are already doing the work. Some of them were born after Perlmutter won the Nobel Prize. They grew up knowing that the universe is accelerating. To them, the cosmological constant is not a shock or a revolution. It is the starting point, the thing they learned in their first cosmology course, the baseline they are trying to improve on. This shift in perspective matters. Perlmutter's generation had to fight against the assumption that the universe was decelerating. Every one of their instincts, built from years of training on the old model, pushed back against their data. Accepting the result required overcoming a framework so deeply embedded it had its own name. The next generation starts with the Nobel Prize result as fact and the current tensions as the problem. They are not asking whether dark energy exists. They are asking what it is, whether it changes, and whether it is the symptom of something even deeper being wrong. The psychological barrier is different. The questions are sharper. The tools available to them are also incomparably more powerful. The surveys of the next decade will generate more precise data about dark energy than everything done in the 25 years since the discovery. Machine learning systems trained on simulated universes will identify patterns too subtle for previous generations to detect. Quantum sensing technologies under development could eventually allow direct measurement of vacuum energy fluctuations that have never been accessible before. The problem that Perlmutter, Schmidt, and Rees handed to physics is solvable in principle. The universe has a specific answer for what dark energy is. That answer exists. It is encoded in the structure of reality and has been since before Earth formed. The only question is whether human physics, with the tools and concepts available to it, can reach far enough to read that answer. The generation working on it right now has better tools than anyone who came before. And the universe has been patient. It has been leaving hints for 25 years. Sooner or later, one of them will crack. If someone explains dark energy, really explains it, derives it from first principles, and confirms the explanation with observation, physics does not just add a chapter, it rewrites several of them. The vacuum catastrophe would need a resolution. Whatever mechanism sets the cosmological constant to its precise tiny value, rather than the enormous value quantum mechanics predicts, would become known. That mechanism would almost certainly have implications for quantum field theory, the framework that underlies all of particle physics. The standard model of particle physics, which describes every known fundamental particle and force except gravity, might need extension or revision. The relationship between quantum mechanics and general relativity would change. Dark energy sits at the boundary between these two theories. A successful explanation of dark energy that derives from quantum vacuum physics would likely require a framework that connects the quantum world to space-time geometry. Some version of quantum gravity would become necessary as a stepping stone. Solving dark energy might force progress on the deepest unresolved problem in theoretical physics. Our understanding of the universe's history would sharpen. If dark energy is confirmed to have changed over time, the entire expansion history needs recalculation. The universe's age, the timeline of galaxy formation, the sequence of cosmic events from the Big Bang to the present would all be revised against the corrected framework. Cosmological history, as currently written, contains placeholder assumptions that a real dark energy theory would replace with firm numbers. Technology would follow eventually. Every major shift in fundamental physics has produced unexpected applications decades later. General relativity enabled GPS, quantum mechanics enabled computers, lasers, and the entire electronics industry. Understanding the quantum vacuum, the structure of empty space, and the behavior of energy at cosmic scales might eventually enable technologies as unimaginable today as a smartphone would have been to Newton. The practical applications are the least important part. What matters is the picture. Right now, humanity's understanding of the universe has a hole in it, not a small gap, a hole that covers 68% of everything. Filling that hole would be the most complete view of physical reality our species has ever had. You exist at a specific moment in the history of the universe, 13.8 billion years after the beginning. on a rocky planet orbiting a middle-aged star, in a galaxy drifting through a web of filaments and voids, inside a bubble of observable space that is slowly, irreversibly shrinking. The physics that built you out of atoms forged in dead stars is the same physics that cannot explain the dominant force of the cosmos. Dark energy makes up 68% of everything. It has been accelerating the universe's expansion for 5 billion years. It will determine whether everything ends in cold silence, a catastrophic collapse, or a violent shredding of matter itself, and we have no confirmed explanation for what it is. That sounds like failure. It is the opposite. Science knows what it does not know. That is not a small thing. For most of human history, people explained the unknown with certainty, filling gaps with gods, with myths, with confident wrong answers that felt complete. Modern cosmology looks at 68% of the universe and says, we found it, we measured it, we proved it exists, we named it, and we do not yet know what it is. That honesty is the engine of progress. The story of dark energy began with a team of exhausted astronomers who thought they had made a mistake, who checked their instruments, rechecked their math, and slowly accepted that the universe had just handed them something impossible, who published their result knowing it would be challenged and challenged it themselves before anyone else could. That process, the willingness to follow data into uncomfortable places and say plainly what it means, is how the broken rule got found, and it is how the next broken rule will get found too. The universe is under no obligation to be simple. It is under no obligation to fit the models built by one species on one planet over a few centuries of organized science. Dark energy made that clear. The Hubble tension is making it clearer. The Webb galaxies are making it clearer still. Every generation of physicists inherits a map of reality. Every generation finds edges where the map runs out. The edges are not a flaw. They are the frontier. They are where the work is. You are here, on this planet, in this moment, at the exact point in cosmic history where the biggest questions have been clearly identified and the tools to answer them are being built. The surveys are running. The data is coming in. The graduate student staring at the anomalous graph might be the person who finally explains why empty space pushes the universe apart. And if they do, they will publish their data, describe what they saw, and hand the next generation a new map with new edges. That is how it works. That is how it has always worked. The universe keeps score, and right now, the score is one broken rule found with more waiting.